their set equals 1. So that's the group in question. And if you notice, if you abelianize, you'll get 3a plus 2b is trivial, and minus b minus 2a is trivial. Those are the relations we had before in our abelian computation. Anyway, this is the fundamental group, or the Poincare group of this example. And what Poincare says itself, the question is, this is a fundamental group, is it trivial or not? It's not so easy to say offhand. You abelianize it, you get a trivial group. So what Poincare said was add this relation. And then it's an easy computation to see that the group with these three relators is the same as the group on A and generated by A and B with these three relators. A to the fifth is 1, B cubed is 1, and this A inverse B squared is 1. And that, as Michael said, is the icosahedral group. The group of order 60. It's non-trivial. So I've taken this group and added a relation to it and got a non-trivial group. So this group is certainly a fortiori non-trivial. In fact, it's the binary form of the icosahedral group. It's a group of order 120 with a center C mod 2. So that's how Poincare produced this example and showed it was not the three-sphere by computing its fundamental group, or the group de Poincare, which he had introduced earlier. This manifold was much studied. It's very important, and has another very beautiful description. It's the space of regular dodecahedra or regular icosahedra in free space. I'm afraid my drawing ability isn't so great, but let's imagine a regular dodecahedron. So its faces are pentagonal, and it's regular. As I say, my drawing is not too good. 1, 2, 3, 4. Sorry about this. Anyway, you go around, here's the central pentagon. Around it you put 6 more. It makes a slightly spherical looking shape with a ragged edge, and you can glue another one on the bottom. You get a regular a figure with pentagonal faces, 12 pentagonal faces. I've actually seen desk weights, paper weights made out of them with calendars on them. Since there are 12 faces, there's a month on each face. The faces are pentagonal. So this is a regular one of the Platonic solids. If you look at its symmetries, so it's got, let's just think about the symmetries of this regular solid. It's got 12 faces, each being a pentagon. By a symmetry, you can move, because it's regular, you can move any face to any other. And once you decide where you're going to send the top face, you can also rotate through 5 possibilities. So you have 12 times 5, or 60 symmetries of this regular dodecahedron. So that's the group I've called gamma 60 here. It's the group of 60 symmetries of the dodecahedron. So I look at the space of regular dodecahedra centered at the origin in a volume 1. Well, you can get any one of those from a standard one by a rotation. But the trouble is, if you rotate by one of these symmetries, as elements in gamma 60, you get back to where you started, but presented differently, ambiguity in the sense that Etienne was using it last night. So the space of regular dodecahedra is, in fact, the rotation group in free space divided out by this group of symmetries. So I called it the space of regular dodecahedra of volume 1 and center of mass at the origin in free space. So it's a beautiful geometric manifold. Another way to think about it is SO3, the rotation group in dimension 3, is doubly covered by the 3-sphere. So this is a quotient of the standard 3-sphere by a group of order 120. It's a group that covers the symmetries of the dodecahedron. So that was Poincare's example. And one point I want to make about this example, I guess I want to make 2 points about this example. It shows why the problem of classifying free manifolds is hard. It also shows why it's tantalizing to try to approach it directly without using vast theories, without using all the power of geometry. You're talking about families of curves on a surface. This is something you can see. Now, and as I've shown you, you can calculate the fundamental group from the pictures of the curves. And the question actually, as Poincare says, becomes, given 2 families of curves like this, so that when you compute the fundamental group, the result is trivial, by a set of elementary moves, which is fairly easy to describe, can you turn this picture into the standard picture? So the picture that will make the 3-sphere, and draw it in genus 2, is this one. So the standard picture that makes the 3-sphere, well, we have this is one family of curves, and this is the other family of curves. If you glue 2 handle bodies together using the yellow curves to make one handle body and the red curves to make the other, you're producing a standard decomposition of the 3-sphere. So given some collection of curves like this that computes the trivial group, this computation gives the trivial group when you calculate the fundamental group, can you, by elementary moves, turn it into this picture? And actually, Poincare, when he formulated the problem, first formulated it is any simply connected manifold equivalent to 3 manifold equivalent to the 3-sphere. He went on to say, in other words, can you do this? Of course, it wasn't until 60 years later that it was understood that those 2 questions were the same. If you could manipulate your diagram to get this picture, then you definitely have shown your manifold is the sphere, but it's not clear that you have to be able to do this to show the manifold is the sphere. There might be exotic ways to make a Hagar decomposition of the sphere, but in the 60s, Waldhausen, I guess, proved that, in fact, it was not, and these 2 questions are completely equivalent, something that Poincare was implicitly assuming. Another interesting twist, it was proven again in the 60s, I believe, that for genus 2, you can always do this. Genus 2 is simple enough that one could resolve the Poincare conjecture, make this transition anytime the group was simply connected into the standard form. But it was not understood how to do it, and still today is not understood how to do it in higher genus. But this is the approach that Poincare suggested. It's tantalizingly visual, and it's purely topological, and for 100 years people tried this and various closely related cousins of this, and were not able to succeed, and still today we have no direct topological argument for this. So after he said all of this, he ends his a 70-page article by saying, "Mais cette question nous entraînerait trop loin." And indeed, it did. It took us through a tortuous path of 100 years, through topology, some of which I want to talk about now, and eventually into geometry and analysis, which clearly Poincaré was trying to get away from in this article. But in fact, even in his own terms, he cheated. If he was studying curves on a surface, he needed to know, if you give, today we would say, if you give an element in the fundamental group, you give a word, how do you know whether or not that word is represented by a simple closed curve or a curve that has to intersect itself? Or suppose you're given two words and you want to know whether or not there's a representative of those by curves that are disjoint. Rather than answering those questions purely topologically, which in fact we know how to do now, he appealed to hyperbolic geometry. So in setting up his purely topological approach to the Poincaré conjecture, he did appeal to geometry to understand the basics about the curves on the surfaces that he needed as input to formulate this purely topological question. So one of the great ironies of this whole story is that what he was doing secretly when he didn't want to tell you that it's some hyperbolic geometry or geometry is in dimension 2 in order to set up his approach in dimension 3 is exactly the same sort of method that resolved the problem in dimension 3. Well, this is 100 years of topological failure, if you will. People attack this problem over and over again, different variants, and basically they always made the same kind of mistake. And in fact, in the 60s, one of the leading topologists wrote an article entitled, John Stalling, How Not to Prove the Poincaré Conjecture. And he starts off by saying, well, I thought I'd prove the Poincaré Conjecture, but that was in another country, and it was a long time ago, so nobody noticed. But to help future workers, I'm going to point out all the standard mistakes that have been made and I have made, so you won't make them. Of course, people continue to make them anyway. Another tantalizing approach to the Poincaré conjecture, again coming from this presentation in terms of simple closed curves on a surface, is a purely group theoretic question about homomorphisms between certain kinds of groups, and that group theoretic question is equivalent to the Poincaré conjecture. You show it to a group theorist and say, oh, I don't know, but I bet I can solve that question. Indeed, they couldn't. So there's something tantalizingly direct about the question, but it seems to be beyond the direct methods. Well, what progress did topology make when attacking this question? And here I want to put up a little diagram. This is in the spirit of Akia's talk, a very superficial diagram, but let's think of this as topology. This direction is dimension, and down here we have 0, 1, and 2. Those were all completely understood, so we don't need to worry about them. Here's 3. That's where things begin to get interesting, and then 4, 5, and then so on. And at this direction, we'll do complexity of the manifolds. I won't try to specify what that is. I might say a little bit about it in dimension 3. So my intuition about Poincaré's approach to topology was, okay, we completely understand all of this. We want to understand more what happens in higher dimensions, so let's start here. This is the simplest. This is the simplest three-dimensional manifold of the sphere. This is the lowest dimension where we don't understand anything. Clearly, it's just going to get more and more complicated as either the manifold gets more complicated or the dimension goes up. So we'll start here. But of course, in the end, we want to understand everything. This is just the first step. Of course, in some sense, it turned out to be almost the last step. So Poincaré got it wrong in both directions. In 1961, Smale did the analog of the Poincaré conjecture, called the generalized Poincaré conjecture, in dimensions 5 and higher. So Poincaré's question about characterizing the sphere in terms of its fundamental group and its homology, well, it turned out to be easier in the higher dimensions than in dimension 3, and Smale did all of them at once. I guess maybe he first did 7 and higher, and then he moved down to 6 and 5, but that left these two dimensions. So the higher dimensions are simpler than the low dimensions. And let me just try to indicate briefly why that is. And Michael's already said it. It's because in dimension 3, there's knotting phenomena. So you can have embedded circles in three-dimensional space or in three-dimensional manifolds that contract to a point. So they can be continuously deformed to a point. They represent the trivial element in the fundamental group, and they're embedded, but they don't bound an embedded disk. If every time you ran into one of those circles, you could find an embedded disk, then you could solve the Poincaré conjecture and do a lot more. In fact, because of knotting, we know indeed that's not true. The analog in higher dimensions, to prove the Poincaré conjecture in higher dimensions, Smale, again using Morse functions, the same cutting process we talked about, realized that, in fact, it's exactly the same problem. It's a problem about circles bounding embedded disks. But now you have lots of room. In dimension 5 and higher, anytime you have an embedded circle, just by general, which is contracts homotonically, just by general position, you can put in a disk. And that was enough to solve the Poincaré conjecture in these higher dimensions. It doesn't quite work in dimension 4 because the disk is two-dimensional, so it might meet itself. So it's very difficult, and of course it doesn't work at all in dimension 3. It's not true because of knotting. So the higher dimensions turn out to be easier to understand by these direct topological methods that Poincaré had in mind than the low dimensions 3 and 4. It's also the case, as we learned in the 60s, that the more complicated three manifolds are easier to understand than the smaller, what seem to be simpler three manifolds, and they're analogs of the Poincaré conjecture for those manifolds, which were established by Haken and then Waldhausen. Okay. To understand these more complicated manifolds, one relied on the work of, in the 50s, of Papakyriakopoulos. So he in fact established results that Poincaré and then later Max Dane were implicitly assuming in the early part of the century. It's again related to circles that are homotopically trivial contractive points and whether or not they bound disks. So what Papa proved is that if you have a compact manifold, you have a manifold with boundary, and you have a circle on the boundary, which contracts inside to a point in the free manifold, then you can find an embedded disk that bounds that circle. It's called Payne's lemma, even though Papa proved it. And then using that, one could cut apart these more complicated manifolds, find interesting surfaces in them, cut them apart, and completely understand them. So in the complexity direction, at least for free manifolds, Poincare was wrong. So these are understood, and the analog of what he conjectured for the three-sphere is true, and this understanding, these theorems, were purely topological. In higher dimensions, we have these purely topological techniques. Dimension 4 is an interesting story, and Michael put up a picture of Mike Friedman. He was able to take Smale's argument from the high dimensions and push it down in dimension 4 to find embedded disks that these circles bounded. But those embedded disks were incredibly crinkled. They couldn't be smoothed out. They couldn't possibly be smooth disks. That was a consequence of Donaldson's work on smooth 4 manifolds. But Friedman then proved this conjecture. So we had the Poincare conjecture and its analog in all dimensions except 3, and we had the more complicated 3 manifold, and we were left with what was originally the beacon, the sample problem, the first test case to try to study, being, in many senses, the last case. And as I said, topology does not, the pure topological arguments do not seem powerful enough to do this. Well, I've now set the stage for the rest of the talk. I think they will all be, in one form or another, much more geometric than this purely topological introduction I've given you. I've tried to explain to you why topology failed to solve this problem, why people continued for 100 years to try to solve it in purely topological terms, why it's so tantalizing. And I tried to indicate a little bit of what did come out of studying this problem, which is a history of topology through the 50s, 60s, and 70s, until geometry began to come into the picture in the late 70s, early 80s with Thurston's work, and then Donaldson's work in dimension 4, and then finally the coup de grace for this problem with Perlman's work within the last 5 years. Thank you. So the next bit is Misha Gromov. So Misha is known for his fundamental contribution to many areas of geometry, so that just mentions the Black-Jones, the hyperbolic geometry, geometrical theory, and many others. So in relation to this conference, let me mention that I think probably one of the first papers by Edelman, maybe the first paper was the joint paper with Gromov and Boraka. Also, let me mention another fact. So yesterday, Bill Thurston mentioned that after some point he was 99% plus sure that Poincare conjecture is true, but on the other hand, as recent as 2002, I think there was a conference somewhere, and there was a conversation, and Misha mentioned that from a certain point of view, the probability that Poincare conjecture is true is close to 0. So, yeah, so. Actually, I explained. I think it's still close to 0, right? But that, I think, is right. The point about mathematics in general is completely the least logical of all sciences. Everything, what you prove, you are proving, is just shouldn't be true, right? So, about that, this painting, yeah, and that's, I cannot make some beautiful painting, but other people try to borrow them from the net, and, this equation usually people ask about ourselves, we ask but this is essentially the last question, is whether or not to know the answer.